Morning, everyone. How you doing? You awake enough yet? Ah, dear. Right. Bit of audience participation. How many of you own any x86 hardware? I saw at least one person not put their hand up. Come on. You can't be that disabled. You're not Steve. You haven't broken your arm yet. All right. How many of you got unreasonably drunk last night and are wishing for the sweet release of death right now? I just thought I'd wake you up a bit. Cool, right. So, hello. I'm Graham Sutherland. I work at Cisco Advanced Security Services. Yes, I know that stands for ASS. Apparently nobody told anybody. Either that or they just didn't care and thought it was funny. So, yeah, I've been a penetration tester. I started at Portcullis almost 5 years ago. We got acquired about almost 2 years ago by Cisco, so I'm still there. And I'm going to be talking about motherboard, hardware, and chipsets, and all sorts of weird things that you can find inside there. So where did this all begin? So White Quark on Twitter, they're pretty awesome. Sort of pointed out that you can just sort of download the data sheet for chipsets, which seems very strange. And yeah, I found all sorts of strange things in there, and sort of started me off thinking, I could start looking into this stuff as well. So the scope of this talk, essentially we're just going to be looking at identifying security issues with modern computer hardware, mostly on motherboards. Essentially just treat it like you're tearing down some IoT hardware. Looking at privacy issues and ownership issues, yeah, architectural design failures, and trying to find persistence on motherboards outside of the hard disk. True fileless malware, buzzword. And the weird things that I found along the way that made me laugh. And there's been quite a few talks on various x86 stuff before. There's been stuff on Intel Management Engine, there's been stuff on AMT, there's been stuff on all sorts of different aspects of hardware, but there's never been sort of an overarching thing that just sort of discusses a sort of wide coverage. So just going to acknowledge a bit of previous work. This is just sort of a select few bits and bobs that I happened to have a read of and I found useful. This is sort of a bit of a disservice to the million other papers and awesome things that are out there. So apologies to those that I've missed, but there's a lot of work out there already on this kind of stuff. So yeah, read your chipset datasheet, which sounds weird. You know, it's not like it's a little temperature sensor or something. It's a massive chipset. It's got all sorts of crazy stuff. Intel just literally does give you a datasheet like any other. It's about 700 pages or something. You don't need any account to download it. It's totally free. Contains all the useful things that you would expect it to find in the datasheet. It's also not that really difficult to understand what's in there. There is a little bit of domain-specific knowledge that's required, but to be honest, it's largely quite readable. And if you get stuck, you know, there's Twitter, there's IRC, and people will help. So section 1, messing with Intel Management Engine. So Intel Management Engine is a sort of subsystem that sits inside the chipset that sort of handles a whole bunch of stuff to do with how the motherboard works and how the system runs, but it also has a whole bunch of stuff allowing it to do things like talk to the internet without the CPU knowing about it, so it can do like out-of-band communications. And this ties into stuff like AMT for like remote management, which some of you may be aware of the recent AMT vulnerabilities that came out around that, and that was quite interesting. I won't be talking about those though today. So the rationale of why you might want to mess with IME, it's always running. It has memory access, which is concerning. It's got direct NIC access, so it can talk directly to the network adapter. And that can be either wired or Wi-Fi. And it can talk out to the internet doing that. Hence why the AMT stuff was kind of interesting. But it's a closed platform. Intel wrote the firmware, and it's not like open source or anything. You can't roll your own. It's all signed. Some of it's kind of compressed or obfuscated. There's not really any sensible way to assess the security of it. So there's a lot of people going, oh, I don't really like this like weird Intel binary blob running on a sort of weird hypervisor always running thing on my motherboard, and they want to get rid of it. So, digging through the datasheet, I happen to run into this piece of information. So, Flash Descriptor Override Pin Strap Status, or FDOPSS. So, this essentially says, put Intel Management Engine into debug mode and unlock the flash, which sounds kind of weird. I was reading through this and went, oh, that's interesting. Why would you be able to put Management Engine in debug mode? And how is that done? It says it's using an external strap, external pull-up on HDA SDO. So the pull-up is just basically a resistor connected between a particular line and a power rail. Let's start looking a bit more. What is this? Flash Descriptor Security Override. So it must not be asserted after manufacturing and debug. It puts it into puts the Intel Management Engine and into a debug mode and disables the ME features. Might be quite useful if you want to turn ME off. So how might I turn this strap on? Well, here's the pin I need to get to. To paraphrase James May, oh cock. It's a BGA part, and there's no bloody way you're getting anywhere near that. However, there may be other ways to do this. Anyway, I thought this was kind of weird, so I posted it on Twitter. And it got a bit of a reaction, which sort of started me off going, okay, people seem to find this kind of interesting, so I should probably look into this some more. So at this point, what did I know? So HDA SDO is the HD audio serial data outline. So your chipset talks to what's is essentially an audio codec. So it's when you've got like 7.1 support or sort of like optical out or any kind of HD audio on your motherboard. There's a separate chip for the codec. The chipset has a sort of serial data protocol that it uses to talk to the audio chip. And for some reason, Intel chose this HD audio line as where they should put the ME debug strap. It sounds kind of a weird dual purpose, but if you... I've written pulling it low at boot. It's not true, it's actually pulling it high. My bad. And IME debug mode unlocks some registers, and yeah, we know that Intel doesn't want to use that functionality because they said don't assert it after manufacturing. But what don't we know? We don't entirely know what ME debug mode actually does because there could be all sorts of things in there that we're not entirely sure. Where can we access HDA SDO? So, I mean, we know it goes to that particular chip, but that could also be a BGA part, and it could be really difficult to touch and be really annoying. And what happens if we mess with the registers that are in there and start messing with the flash as well? Someone else to the rescue, which is always great. Basically, look for prior research whenever you're looking at this kind of thing. Turns out none of this was new. People knew about this. The LibreBoot and Core Boot folks and the people who wrote ME Cleaner already knew about this stuff. They'd already known about HDA SDO. They knew it stops IME from executing, but unfortunately it breaks the integrated gigabit NIC. The reason for that is that the gigabit NIC it has its own special control channel from the chipset so that it can do all the management engine stuff. And in the process of the boot sequence, the IME is what sets all the hardware configuration variables for the gigabit NIC. So if you turn the IME off, guess what happens? It doesn't configure the NIC and it doesn't work, which is a bit of a pain. And it also sets a 30-minute shutdown timer if you assert this strap. So what happens is it boots up and it goes, right, IME is off. And it goes, right, well, because I'm not running anything, I'm not able to control anything. So therefore, after 30 minutes, I'm just going to hard power off the system, which is annoying. And the IME sectors in the flash are signed, so you can't muck with them easily and start messing with the firmware, sort of. So, neutralizing IME. If we can't just kill IME, can we make it not do things at all? So if you find the HDA SDO pin on board, you can, I keep saying pulling it to ground. I've written this wrong. It's pulling it to 3.3 volts, I think, to assert the strap, boot the system, dump the ME firmware flash from map memory, because it does get mapped into memory that the operating system can read. Neutralize it with ME Cleaner. So ME Cleaner is a bit of open source software that basically goes through, and they worked out that you can actually wipe most of the sectors. So it's like a partitioned firmware table. And then there's the signing data, and then each partition is individually signed. Idea being that if a vendor wants to add a new partition, they don't need the Intel signing keys to sign all of Intel stuff again. It's all separately signed. It turns out you can actually wipe a lot of those partitions out, and ME will still boot, clear the timer, so it won't do the 30-minute reboot, and it won't actually do a whole lot. Unfortunately, it did very, very variant depending on which laptop you're running it on. I don't think anybody's done anything with any desktops yet. And the laptops that this works on is like old IBM ThinkPads, so you know, like the old T40s and stuff. So there's not really any particularly modern gear that you can do this with. And then you write this neutralized image back to ME Flash and then reboot, and it should just work. Now, the other option, this is actually the option that most people choose. Find the ME Flash device on the board, which is an 8-pin SPI flash chip. Just desolder it, or use an IC clip, but usually desolder it. Use flash ROM to dump the flash, neutralize it, and then write it back, and then reboot. So the ME cleaner approach, as I described. The ME firmware is split into partitions. Partitions are signed, but the FPT, the firmware partition table, is not signed, which means that you can just remove the partitions. You can't remove the, as I've said, the only partition that can't be removed is the factory partition. There are some cases where that's not the case. There are a couple more you can't remove, but in general, you can neuter IME fairly well this way. Now, the problem is that these kind of require you to mess with hardware, and people who want to sort of lock down their, and sort of own their own device and not have this weird Intel thing running on their system, would quite like to do this, and it would be very convenient to not have to sort of open up your laptop and get to the motherboard and start faffing with, you know, soldering things on and or, you know, desoldering ICs and things like that. So the problem is, no motherboard designer would ever expose IME straps in a way that we might abuse, would they? Or would they? So what you're looking at here is a circuit. So if you ever want to know what your laptop looks like in terms of a schematic, chances are it's all been leaked online. Motherboard repair is a fairly big industry, and in the States, right to repair has been quite useful for this. So you can download the schematics of pretty much every laptop out there. For some reason, it doesn't work the same on desktop motherboards. I think people just see them as more of a commodity to throw away, whereas a laptop, it's much more difficult to sort of justify that. So in this case, what you're seeing is, where are we? So the ME unlock pin that you can see in the middle, it's in, well, I was about to say it's in the green square, but everything's in the bloody green square, goes to the HDA SDO line on the right, on the right, and then you've got this sort of interconnect on the left here with these two resistors, and then at the bottom, we've got this ME unlock pin, which is connected to the keyboard controller for whatever reason. And then Toshiba did this, where you've got the keyboard controller, again, talking to, where are we here? Yeah, we've got it talking to this debug trap again. And then we've got this one. Oh, hang on a minute. Did I just... Oh, sorry, yes. Yes, this particular strap, again, allows the keyboard controller to disable IME for whatever reason. Oh, excuse me. And then we got the same kind of thing again for Acer. Thank you very much. Oh, and this one was particularly great because when I saw the ME unlock, these question marks were actually put in by whoever reviewed the PDF, reviewed the schematic. So clearly they were as confused as I was and just like... What the hell are you doing here? Why is that? What's happening? This is very strange. Yeah, so there were a lot of question marks there. That made me laugh quite a bit. And this one was particularly weird. This is like some very sort of obscure x86 platform for network hardware. And yeah, it's slightly strange. They have a jumper exposed on the board where you can just plug in a jumper and it just turns an ME debug on. It's very strange. Then we get into things that are broken not by a sort of design weirdness, but by specification. So this is where you sort of get into this interesting area of where Intel have gone, right, well, what we need is we need a line, a data line that nobody's going to be really paying too much attention to use as this debug strap. And we'll cross-purpose that for, I don't know, let's HD audio, that'll do, screw it. And then the HD audio spec says, oh, actually, you can expose this HD audio data pin externally to the laptop. So the hot attach mechanisms are designed to allow the audio codec IC to not be on the laptop motherboard. You can have it in a dock and then have that be communicated with over the docking connector. So the idea was assert the ME debug strap via the docking connector on a laptop, so we don't have to disassemble the laptop and start soldering on things. Unfortunately, docking connectors are proprietary. They change between laptop models. They've got all sorts of very strange formats. They all seem to be different for everybody, and it's very annoying. And unfortunately, it doesn't look like anybody, well, from the 180-odd laptop schematics that I sat and trawled through, I couldn't find a single one that exposed anything on the docking connector, which was unfortunate. So the future work for this part is trying to identify and document convenient locations to interfere with IME and find a way to restore the gigabit NIC without ME access, which would be quite nice. Except somebody found a better way. So about a couple of weeks before this talk, as is always the way, I spend ages doing a whole bunch of research, and two people come along and nullify it all. Hey JP, high availability platform. These two guys, Mark and Maxim, discovered that there's a hidden flag inside this this sort of Intel configuration thing called high availability platform HAP. And essentially the idea is that their power customers, their high-end customers, can configure very specific behaviors that the chipset and processor configure various behavior for those things. And there's an undocumented flag in there that entirely disables ME, and you can do it all from software. It's now been released into ME Cleaner. It still breaks the gigabit NIC because it doesn't allow, obviously it's the management engine that sets that up. So there's still some future work to be done in terms of identifying a way to restore the functionality of the gigabit NIC. But now you can disable ME from software, and that invalidated pretty much everything that I just talked about. Thanks, guys. But it is kind of cool, and it means you don't need to disassemble the motherboard, disassemble the laptop and start mucking around with the motherboard. So let's move on to some architectural issues in laptop motherboards mostly. So the chipset has a few privileged buses, and they talk to various peripherals for various reasons. These are privileged because you don't want other things interfering with stuff that's on there. So for example, the keyboard, the TPM, and the NIC. These are quite important devices, and you potentially don't want them sharing a bus with other devices. So how do we find them? You look at all the motherboards. It's expensive to buy every motherboard laptop and start tearing it apart and manually looking, and it's also a pain in the arse. So you just use the leak docs. So you right to repair for the win. So I spent hours and hours and hours and hours and hours looking through various laptop schematics, and then ran into this. So the DIMM socket has these two pins, SCL and SDA, so therefore the SM bus, which is a system management bus, and they're also connected to the LAN controller. Why is the DDR socket connected to the LAN controller? Because we know the LAN controller can be controlled via, LAN can be controlled via SM bus because that's how IME talks to the internet. So this is very strange. And then, why does my RAM have access to the Wi-Fi? This is not the same motherboard. So yeah, finding a few laptops where they'd made this weird mistake where they'd essentially shared the SM bus from the memory sticks to the Ethernet controller or the Wi-Fi controller was very strange. So I propose a new concept. The Internet of DIMMs. So what is this this SN bus on the memory devices on the DIMMs? What does that talk to? So it talks to this thing called serial presence detect (SPD). So it's an IC on each DIMM that stores things like RAM configuration. So if you've ever done any overclocking, you know things about timings, like you'll get timings like 55515. These values and lots of other detailed bits of information get stored in this SPD chip. The standards body for this is JEDEC, and if you read through the standard and look at what's in there, it gets kind of ridiculous because they've got things like the physical dimensions of the stick inside the SPD, which is a little bit weird. It's like, why does my motherboard need to know exactly how big my RAM chip is? This actually starts to make sense in like compute cluster because you need to know like heat management stuff, but yeah, it should be an SN bus slave device. But SN bus is multi-master by design. So what I mean by slave device is that the PCH, the chipset, is the bus master. It controls who can talk to who, and it essentially asks for an SPD device to give it some information, and it gives it back. But SN bus is multi-master by design. So what if that SPD chip decided to become bus master and start talking? So what's stopping it? Not a lot. So that's what an SPD chip looks like. The thing circled in red. So you've got a stick of RAM and this tiny little 8-pin chip. And the 8-pin chip is essentially just a bit of flash. So an SPD IC is just an EEPROM. So common ones include those things there. I'm not going to read them out. They've got fairly ubiquitous pinout, so they're kind of standardized, even though they're made by different manufacturers. So you've usually got 3 address select pins, a ground VSS, SDA and SCL for the clock, data and clock, a write control pin, or in some cases the write control pin isn't present and it's just a non-connected pin, and VCC for power. And coincidentally, an AT-Tiny85 microcontroller has a compatible pinout. So what if we made a microcontroller that pretended to be the SPD? So at the top there, that's an SPD IC. So you've got these E0, 1, and 2. Those are the address select. You've got the VSS, which is your ground, VCC, which is power, WC, which is write control, and SCL and SDA, which is for the SN bus. And then if you look at the bottom, you've got the VCC and ground in the same positions. The address selects you generally don't need to worry about, and on the positions on the bottom right, the SCL and SDA pins just happen to line up with pins on the AT-Tiny85 microcontroller that support interrupts, which makes it really easy to write software SN bus. So the approach is replace the SPD EEPROM with an AT-Tiny85. So you've got a RAM stick that actually is backdoored in a weird way. I should point out that the SPD does not have access to the data that's on the RAM stick. It's completely separate to that. So you write an interrupt-driven SN bus listener on those PB0 and PB1 pins, and when you want to swap it over into an evil mode, it becomes the SN bus master and starts sending network packets via the IME. So suddenly your DIMM is talking to the internet. So what's the status of this at the moment? Well, I have a fake SPD working. Unfortunately, the SPD master code, SN bus master code, I haven't completed yet, so I can't demo Nick talking, the DIMM talking to the internet just yet. I'm really sad that I haven't got that far. But the plan is have a magic value sent to the SPD via the operating system. So in this scenario, you will have routed the operating system, but what you want to do is have a surreptitious sort of covert channel out, and you can essentially do that directly via talking through this. It's not a particularly feasible attack, but it's funny, and that's why I did it. So I've worked out some of the NIC commands. It's ongoing development. No demo on that bit yet. However, if I've got time at the end, I will show you a quick demo of some funny stuff that you can do via the SPD. Yeah, hopefully I've got time for that. So, section 3, persistence. So, what if you want to persist data but not on the disk? Well, what have you got access to? Well, there's the UEFI BIOS. There's the IME firmware. We know we can mess with that in some scenarios, but it might be a little bit difficult. SMM, that's tricky. there's some research that's gone into that, but they really, really don't want you to get access to that from, running even from ring naught. Peripherals. So, yeah, there's all sorts of peripherals, and that can be things like disks, that can be things like graphics cards, RAID controllers, Ethernet controllers, anything like that. RAM. Can you do non-volatile persistence on RAM? Maybe. And other ICs on the motherboard. So UEFI BIOS, it's user flashable, but the updates are usually signed. The data persistence is possibly it's kind of possible via empty config sections and other sections of the flash that just aren't used. But it's a quite targeted attack, and the failure state is you brick the motherboard. So if you're trying to be sort of subtle and hide, maybe bricking the motherboard is not the best way to go. Of course, the IME firmware, again, physical access required to flash it, which is a pain in the arse. Some regions are OS accessible if you mess with the Intel flash descriptor. Some of the partitions are Huffman coded, but that's been reverse engineered. I didn't know that until quite possibly like 2 days ago, and a guy called Nico H told me that's been done. So this is potentially useful as a sort of persistence mechanism for data. SMM, it ain't happening. There's a lot of research there. There's very, very new results suggesting that there may be ways to write and dump SMRAM, but potentially not, probably not persistence in that scenario. So I'm just going to skip over this because I don't know a whole lot about SMM, to be honest. Peripherals. These are great. So GPU, NIC, SSD. How many of you here have updated the firmware on any of those three ever? Cool. Yeah, so quite a few of you. Yeah, so you can update your SSD firmware, you can update your Ethernet controller firmware, GPU firmware. So they're all user upgradable. The checking of signatures is variable, and in a lot of cases, they only check the signature of the length of the data that you specify in the header of the firmware. So the slack space of the flash device, you can just use however you like. So it's potentially useful for storing secrets. So for example, if you're trying to do the whole like fileless malware thing and somebody comes along and does a memory dump, well, what if all of your keys to decrypt the stuff that you left in the memory dump were in the GPU firmware flash? They ain't getting that. So that'd be quite interesting. RAM. No, not the volatile bit. The SPD flash is read-writable from kernel space. You can actually flash it. And it's known to be an exfiltration vector, and I will explain that one in a minute. So yeah, the slack space and the unused fields can be used for secret storage. And you can I have actually got a working case of cross-site scripting from the SPD flash, which is the demo that I will show later if I've got time at the very end. So when I say known to be an exfiltration vector, I had a very interesting chat with a chap who works in secure hardware reuse. He does some very interesting low-level stuff. And his clients are the kind of people who care about this kind of thing, like surreptitious data being stored surreptitiously into various bits of hardware on their machines. They're the kind of people who will pay somebody to spend quite a long time researching this sort of thing. And he was involved in a scenario in which somebody had a single window of opportunity to install a piece of software onto a system which they should not have had access to. They were attempting to gain access to some key material, so they dropped a USB device into this system, installed a piece of code, and then left. And later, what happened was the box went down for a scheduled reboot and didn't come back up. And what happened was they went, oh, okay, what's wrong? The server then said, oh, you've got a RAM fault. So they took the faulty RAM stick out and they put it in to be RMA'd. So it went to the post room. And then the guy tried to steal the RAM stick out of the post room and got caught. If he hadn't have been caught, then they would have never known that he'd done this, but the SPD flash was completely overwritten with the key material that they were trying to steal. So they used a stick of RAM as an exfiltration mechanism, which is slightly scary. I imagine that the kind of person who was wandering around in a postal room was possibly not also the person who wrote this fantastic piece of exfiltration nutcaseness. And I'll leave it to your imagination as to who might have that kind of capability. It's a very, very weird situation. So other motherboard ICs, the chipset has scratch registers. So chipset drivers often use these scratch registers. They're quite similar to CPU registers, except they're usually bigger. So a few, maybe like 512 bytes or so usually. So these are volatile registers, but the kernel can write to them. They don't exist in CPU space. So again, if you're trying to hide something out of RAM, PCH scratch registers are quite interesting. RAID controller firmware, that's fun. If you've got RAID controller on your motherboard, just write data that you want to hide away inside of that. There's non-volatile flash-based sensors. So a lot of the time, things like your temperature sensors on your motherboard actually have EEPROM in them, and you can write to that. So again, another place to hide it. And hard disk environmental logging, so telemetry data. So who here has bought a hard disk from Western Digital, like one of the black, red, or whatever series, and read where they say, oh yeah, you can't put that, we won't honor the warranty if you put this in a RAID array, so not the reds, the greens and the blacks and whatever. Well, the way they know about that is that write patterns and things are categorized and stored as telemetry data onto an EEPROM chip inside the hard disk. They also log things like temperature, min-max, things like that. It's like smart data, except way more detailed. And this is also where the smart data is stored. So yeah, the hard disk actually has a whole bunch of flash on it that you can just write to live. Do not ask vendors how to mess with that, because they get really cagey and upset, because they assume you're trying to screw them. So secure reuse. This is an interesting sort of field of research that's starting to sort of grow in size. So in some cases, if you are reusing bare metal hardware, for example, if you are selling dedicated servers, you're renting them out, and then you want to reuse them for another client, well, what's to say that the previous system didn't store a bunch of weird stuff or modify firmware in some way? So modifying firmware, exploitation of firmware via modifying data, and exfiltration and other contamination of sort of persistent writable devices on the motherboard and peripheral hardware. So the approach here is work with motherboard vendors and peripheral vendors to identify where non-volatile storage exists on a system, and then dump the contents of those devices as a known safe sort of set. This is before any customer ever touches it. Boot, use the system, reflash, verify the writes and check the stability. So check that once you've booted the system once and then you go back and reflash it, you don't brick your motherboard. And then you store this known good state and restore it before it crosses any customer boundaries. So once you've moved a different customer onto this hardware, before you do that, you restore the known good state. And there are a lot of challenges here. So as I mentioned, that vendors are potentially unhelpful. It helps if you've got a good relationship with them, but HDD manufacturers do not like it when you mess with the telemetry flash, because that's essentially their golden ticket to telling you that no, we are not going to honor your warranty. And you need to validate the state before the first customer use. You can't sort of go, oh, actually, yeah, this sounds like a really big problem. We should go and create a known good state from this hardware that the customer's been using for the last 4 years. You can't be retroactive about it. It's got to be done ahead of time. It's also laborious. You've got to go through and verify a lot of flash stuff, and there's a lot of effort involved, and you've got to do a lot of work with the vendors. And yeah, the potential failure state is that your hardware is bricked, so that can get expensive real fast. And yeah, loss or compromise of the known good states is catastrophic, so you've got to be careful about that as well. So solutions to this are having good relationships with your vendor. So in the case of server hardware, people like Supermicro, if you're a fairly big company, then chances are that you may well have a good relationship with them or be able to build one. If you're a mom and pop shop, chances are you're probably not going to have the money to do this in the first place all the time. So yeah, early identification of risk. So invest early in this kind of thing and plan appropriately and automate where possible. At the moment, there are no, as far as I'm aware, there are no like open source tools. There's no framework for this. There's no, there's no standard. The people that I know that have done this have built hardware interface jigs. So essentially, big 3D printed set of stuff connected together with test probes that moves across and gets put on top of the motherboard, and it connects to all the right positions and does all of the testing. Again, this is months and months of work to build these things and a lot of effort. But it helps reduce the manual effort, so it's always good. And having a clear procedure and multiple validation and verification checks, so validating that things have been flashed correctly and verifying that that data is correct. And that can help eliminate potential bricking of your device. And secure and redundant storage of the known good states, because if you've got a known good state, but you put it on an SMB1 enabled box somewhere, that's no good. Best case, somebody ransomwares it, encrypts it, and you lose it. Best case, somebody comes and mucks with it. Worst case, somebody comes and mucks with it. So, conclusions about this. You should look at your hardware data sheets. Chipset, processor, anything like that. It's really not that difficult to start digging into this stuff, and it is a good laugh. You find silly things in there. And yeah, vendors don't always follow good practice in design. Supply chain attacks, they don't necessarily need to be a target of the security critical devices. So you don't need to do a supply chain attack on the TPM. You don't need to do a supply chain attack on the processor. You don't need to do it on the PCH. You can do it on a stick of RAM, which is much easier in many cases. And secure reuse of hardware is really difficult. There's a lot of effort going into that in certain spaces, but I doubt we'll see it become particularly common. And it is quite concerning to think that every single, there's probably quite a few laptops in here, two just here, that they're just full of writable devices that just nobody really thinks about writing or securing or looking at. So I'd like to give some special thanks. White Quark on Twitter, Tim Brown, because he bought me this laptop that if I've got time, I'm going to show you a demo on. The anonymous hardware security guy who told me all about that interesting little exfiltration trick. Nico H and JN on Core Boot, and lots of people from LibreBoot who helped a whole lot in me understanding some of these things. How am I doing for time? Oh, 15, wow, okay, I finished that quick. Damn. Okay, so who wants to see a demo? So, oh God, this is difficult. Can't see my mouse. Where's my mouse? Here we go. Right, so this is this laptop down here, which is of a non-specific make. I won't tell you which one it is. I'll just say that if Doge owned a laptop, he'd probably own that one. Am I clicking the read button? I think I'm clicking the read button. I don't know whether you can see here. I think that right there says Sutherland because I've modified so the RAM stick in here does not have a normal SPD flash. It has an 80-tiny-85 instead of the flash. So when I wrote the data into that, I changed it. But it also turns out that you can modify it. God, this is really difficult. I can't see. Here we go. Right. So what happens if I change the module part number to something a little bit more interesting? So this is modifying what's on the SPD flash. So what if I put an iframe in it? and then update. Huh. Huh. And then if I write that to the device, so this is written to the EEPROM. I'm really, really sad that this system does not have like the old school boot sequence where you can see all of the data that's going on. It's got one of those crappy like splash screens that you can't turn off, because I would have loved to see whatever arbitrary text I put in there spin up at the start. That would have been very funny. So if I close this software completely, that bit of data that I've just written is in the RAM. If I were to, let's say, swap out your regular RAM stick for this RAM stick, and then I were to, oh God, I can't even see what I'm doing here. No, that's not what I wanted to do. Of course, for this kind of thing, you have to break out the finest in overclocking tools. And there we go. So that's come back from SPD flash. So that RAM is now backdoored with an XSS for this particular tool, which is the most ridiculous attack on the planet because nobody will ever fall for that and it will never be useful to anyone, but it made me laugh. So yes. Yeah, fun. Right, let's Hey. Right, and that's pretty much it. Any questions?